All right, everybody. Today we're going to talk about polynomial functions. And actually, this particular section in the book is really a long section. It's called Polynomials and Rational Functions. So I'm going to split it into two videos. One will be polynomial functions. The other will be the rational functions. I think in your homework there's one for each. So what I did was I split it up so that there were problems about polynomials and there were problems about rationals, and they're two different homework assignments. So just be aware of that. So first of all, let's start with what are we talking about here with polynomials? So technically, if you look at the word polynomials, the word poly means multiple. Okay, if you look down at it, and the word nomial, it's like the Spanish word nombre, which means naming, okay, or your name. So this comes from the Latin, the same root as that. So this is multiple names, or in our case, it means multiple terms. Okay, so a polynomial is just a function that has multiple terms in it. Okay, and that can be a little misleading because there is something called a monomial. Mon meaning one, singular. So you do have stuff that just has one term, y equals 5x squared. That's a monomial, right? Monomial. Sorry. Two M's, one N. Okay, it's a monomial. And sometimes whenever we deal with stuff, we'll do factoring or something like that. X squared minus 16. That's a binomial, right? Okay. So the thing about it is binomials are still part of the polynomial functions. They just have a very specific name. Monomials are still part of polynomials. They're just specifically one term. So most of our stuff is going to be multiple terms, right? Okay. So something like y equals negative 3x squared plus 5x minus 22. There we go. Okay, that guy has three terms, and he could be called a trinomial. Okay, just like mon is one, bi is two. He could be called a trinomial. But once we get past trinomials, we just start going, hey, I don't want a new word for every time we do this. So basically, all of these act and function in similar ways. And so we just kind of lump them into this family of functions that we call polynomials. Okay. That's how the mathematicians deal with them. And again, we're going to talk about things with multiple terms. The monomial, I mean, he's out there, but he's kind of boring, right? So we want stuff that's more interesting than that. So when we are talking polynomials, they're probably going to be more than monomials. Not always, but probably. Okay, so equation with multiple terms. There have to be a few little caveats about this. So our equation has to have all positive integer exponents. Okay, and we'll see in the next little video why they're not, if they're not positive integers, they're not polynomials. They fall into a different category. Okay, and then we also have to have all coefficients are real numbers. Okay, so what does that mean? It means I can't have any imaginary numbers in there for my coefficients, which we don't normally deal with anyway, but they are out there, so we have to say, don't use those. Okay, so we're not going to use those. Don't consider that stuff. So here we go. Let's look at the stuff I already talked about. The exponent here is a 2. Is that a positive integer exponent? Integers are like 1, 2, 3, and then all their negatives, right? But we're saying we only want positive integers. Okay, so yeah, that's a positive integer. No problem. We're good there. Okay, so actually, I should say, let me not say positive. Let me say non negative. That's a better definition. I'm sorry. So non-negative. Why do I want them to be non-negative? I'm trying to be a little bit specific here. And the reason is this next guy right here. This one has a 2 for the exponent here, but there is technically an x term here with the 16. What's the exponent on it? It's a 0, Dr. Webster. Because in your exponent rules, and if you haven't yet, I've got a review about exponent rules. So again, that should be prereq material. Hopefully you've seen it. But if you haven't seen this before, x to the 0 is a 1. In fact, anything to a 0 is a 1. So 16 times 1, it doesn't change the value here. But so we're going to say x to the 0, and 0 is not negative. So that's why I changed that, because he's out there. Okay. We don't really think of him very often, but he's not a positive integer. He is a non-negative integer. 0 is not positive and he's not negative. Okay. What about the coefficients here? 5, is that a real number? Yes. The coefficient out here, we don't write it, but it's a 1. Is that a real number? Yes. Negative 16, is that a real number? Yes. Negative 3, positive 5, negative 22. All of those are good as far as coefficients. The exponents here are a 2, a 1, and this guy is an x to the 0. So yes. Okay, so all these things are what we would normally deal with, right? So there's nothing crazy going on here. So let's see what we're not talking about. Y equals negative 3x to the negative 4. Okay, so I look at this guy and I say, hey, the coefficient is a real number. That's fine. But what about this exponent? That's negative, right? Okay, so it has to be not negative, right? And in general, we're going to look for positive exponents here. Okay, so I look at that and I say, oop, that's not that's not positive. So this is not a polynomial. Okay. How about this one? Y equals negative 5x plus 10. What do you think about that one? Well, we have an x to the first power here, right? That's okay. This is an x to the 0 power. That's okay. What about these coefficients? Negative 5 and 10. Yeah, those are okay. Those are real numbers. So this guy is a polynomial. So literally what you're going to be doing here is you're going to be looking, and you're going to be looking for the things that make these equations have issues, right? So things that are going to make the equation have issues are if the exponents aren't positives or zeros, basically, and whole numbers, right? They got to be integers, they can't be fractions. And if these coefficients are imaginary, so they would have an I in them. Okay, so that's what we're looking for. Let's do one more so we can see it. Y equals x to the 1/3. Okay, so is that a not negative integer? No, this is not an integer. This is a fraction, right? Okay, so since it's not an integer, this would not be a polynomial. And just as a refresher, again, you're going to be working on some of these reviews about exponents. What is this guy? This is actually y equals the cubed root of x, and I'll get more into that later, but work on that exponent review and make sure you know. Anytime I have a fraction, that guy came from a radical, right? Okay, so these are radicals. These are not polynomials. And by the way, this guy with the negative exponent, he was a rational. He's going to be a fraction. So we'll come back and deal with those later in the next video. But just so you know, those things not okay. All right. So the other piece of information that we know about these polynomials is that all of the graphs of polynomials are smooth and continuous. That's what we say, smooth and continuous. Smooth and continuous. Okay, what does smooth mean? Smooth means I don't have any sharp, jagged edges. Okay, so smooth is like a parabola. We think that guy's nice and pretty, right? That's why I said he can't have a V. He's not a V. He's not a sharp, jagged corner, right? So smooth. Continuous, what does that mean? That means when I draw my graph, I never pick up my pen. Okay. So there are functions out there that are piecewise functions, right? Okay, we can put pieces together and that's fine, but those are not polynomials. Okay, so smooth and continuous. So let me just give you a couple of graphs and we'll see what you think. Okay, so here we go. I'm just going to draw them and you decide what you think. X and Y. This guy looks like this. We'll come back and talk about them in a second. X and Y. This guy looks like this. X and Y. This one looks like this. X and Y. This guy looks like this. Oops, I didn't change colors, sorry. You get the point. There's my graph. And let's do one more. X and Y. And this guy looks like this. All right. So what do we think? Let me come back to this beginning. Is that graph smooth, meaning it doesn't have any jagged corners? Yes, Dr. Webster. Is it continuous, meaning I didn't have to pick up my pencil to do it? Yes, Dr. Webster. So is it a polynomial? And the answer is yes. It's a polynomial. Okay. What about this one? Is it smooth? No jagged edges? Yep. No corners. Is it continuous? Yep. So it's a polynomial, right? Okay. What about here? Oop, there's a jagged corner, right? So things that are like absolute values and stuff like that, they have cusps or corners. This is not a polynomial. Okay, we know it because we see that V shape. And then this one, this is actually a cubic equation, right? It goes 3 different directions. Is it nice and smooth? Yes, no corners. And is it continuous? Yes. So again, a polynomial. Okay. And last but not least, here I have this guy. And literally when I drew him, I drew this piece and then I picked up my pen and I came up here and I started over and I drew this piece and he's called a piecewise function, right? He has 2 pieces, literally is how we say it. Okay. And he is nice and smooth, but he is not continuous, right? So that makes him not a polynomial. Okay, so that's how we know. Is everybody okay? Think about it for a second. Let me know if you have issues. All right, so here's where we have like an actual definition for a polynomial. They have this format. It's a function, okay? And the function looks like a sub n times x raised to the n plus a sub n minus 1, I'll talk about it in a second, times x to the n minus 1 power plus all the way down until we get to a sub 0. Okay. So what does this mean? Okay. You've got your first coefficient, and it goes with whatever exponent this guy has. So maybe this is x to the third, okay? And then we have the next coefficient, so we go down by 1 on the subscript, okay? Second coefficient. And he goes with x to the, if this was a 3, then this is 3 minus 1, right? Okay, so that would be a 2. And then we'd have some term with x to the first power. And then way down here, this is a sub naught, which is just a constant. And he technically goes with x to the 0 power because those match, just like these match and these match. Okay, but what do we know about x to the 0 again? Anything to the 0 power is a 1, right? So we don't have to write that. That's why it's not part of the way the thing looks, okay, the way the equation looks. So what does this tell me? It says I'm going to start with the nth degree, okay? Remember, degree is the largest possible exponent on your variable, and I'm going to work my way down until I get to some constant, okay? So we're going to do a couple of practice problems, and we're going to see what we got. So let's see how it goes. Okay, here's an example. We're going to answer several questions about this. F of x equals 7x plus 21. Okay, I want to find the degree. Okay, the degree is the largest exponent in your equation. Okay, so y'all tell me what the largest exponent in the equation is. Okay, and in my head, I hear you saying it's a 1 because the x, and it's always the exponent on the variable, right? So the x there is raised to the first power. So here degree equals 1. Okay. And then we're going to do a couple of little things that we've done before. So how about the x-intercepts? Okay. And again, you know that to find an x-intercept, you plug in y equals 0, but that'll mean making that whole thing equal to 0, right? 0 equals 7x plus 21. Some people say set the equation equal to 0. That's the same thing. Okay, so to solve for x, I'm going to subtract 21. 7x equals negative 21. And then to get that x completely by itself, I divide by 7. And here I go, x equals negative 3. Okay, so I have, remember what we said before, the degree is 1, the most x-intercepts you can have is 1. That matches, right? Okay, y-intercepts. Remember, it's the opposite variable equals 0, so we're going to make x equals 0. So here we go. F of x equals 7 times 0 plus 21. So I plug in x equals 0, and voila, I get y equals 21, right? Okay, there's my y-intercept. Again, you can make it a point. I'm just going to say y equals 21. Okay, the next thing that they ask me is this a polynomial? Okay, and remember, I need 2 things for it to be a polynomial. So let's go look. Is the exponent not a negative integer? Yes, it's a positive integer, so that's okay. Are the coefficients real numbers? Yes, they are both real numbers. So I don't have any fractions in the exponents. I don't have any negative numbers in the exponents. So this guy is a polynomial. Okay. And then there's one more thing that we need to talk about, and I already kind of mentioned it when we were doing quadratics, but just to make sure, let's talk about the maximum number of turning points. Okay, the maximum number of turning points. When we had quadratics, there were two directions. That equation went in two directions, right? 1, 2, which made it have a most one turning point, right? Well, this guy that we're looking at here, this has exponent of 1. That makes him linear, right? If I were to graph this, you could use your calculator, whatever. He's going to be a straight line, okay? But the thing is, his degree is 1. We already said that, right? Degree equals 1. So what did we do here when it was 2? Okay, if the degree equals 2, the maximum turns equals 1. What did we do? Subtracted 1, Dr. Webster. Yes. If the degree equals 1, that's the case that we're in right now, we want to subtract 1 again. So the maximum number of turns is 0. 1 minus 1 is 0. That should make sense, right? Because this is a line. Does a line turn on us? No. So there are no turns in a line. The maximum number of turning points is 0. All right. So let's see another one. I'll let y'all work on it. Okay. Let's see what we got. Sorry, those papers don't want to come apart. Papers, come apart. Here's your example. F of x equals 5x to the 6th plus, I'm sorry, I'll come back to this one. It'll be okay. F of x equals x squared minus 5x plus 6. Let's do that one. Okay, you work on this one by yourself. I want to know 3 things. I want to know the degree. I want to know the maximum turning points. And I want to know if it's a function. I'm sorry, a polynomial. Okay, so push pause, work on it for yourself. Just a minute, won't take you long. And let me know what you think. Okay, hopefully you push pause. You got the answers here. What's the degree? It's the biggest exponent on the variable. So it's a 2. What's the maximum turning points? It's the degree minus 1, right? Degree minus 1. Okay, so 2 minus 1 is 1. And do you think it's a polynomial? I think it is. Okay, there aren't any negatives or fractions up here in the exponents, and all of these coefficients are real numbers. No i's involved. Okay. All right, so let's do the one I started to do a second ago because I want us to do that one together. I wanted you to work this one by yourself. This one I want us to do together. F of x equals 5x to the 6th plus x to the 4th plus 4x to the 8th plus 10. Okay, same stuff, but we're going to do it together. What's the degree? Be careful because the degree is the largest possible exponent on, or the largest exponent on the variable, and this guy is out of order, right? So remember I said earlier descending exponent form. If it bugs you to see this like this, you can rearrange, right? The descending exponent form would be the largest exponent first. That's the guy with the 8. And then the next, which happens to be the one with the 6, and then the next, and then the next, right? So if you don't like the way this one looks, rearrange it first. That's fine. Okay. You're going to see that sometimes they do that in the homework, and it's just to see if you're paying attention, basically. So with this guy rearranged, what's the degree? I think it's an 8. Okay. What's the maximum turning points? It's the degree minus 1. So that's 7. So in other words, if this guy, let me just kind of sketch a graph. 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's going to look something like that. That's the maximum turning points, right? 1, 2, 3, 4, 5, 6, 7. There would be 8 directions. The degree is an 8. That's 8 directions. The maximum turning points would be 7. By the way, let me just kind of throw a line through here. Let's assume it's horizontal. I know it's kind of tilted. How many x-intercepts would there be if this was the x-axis? 1, 2, 3, 4, 5, 6, 7, 8. That goes with the degree, right? There's degree 8, and there's 8 x-intercepts. Okay, that's the maximum number of x-intercepts, because quite frankly, whenever we get up big like that, the 8th degree, some of these are going to flatten out and they're not really going to be turning points. So we won't have as many x-intercepts, and we'll see some stuff like that maybe a little later. Okay, so we got degree, we got the maximum number of turning points, and then the next question is, do you think it's a polynomial? And my answer is yes. It doesn't matter that it looks kind of crazy like that. In fact, this is a pretty smooth and continuous graph, right? So one of the ways we can determine if it's, if it's a polynomial is with a smooth and continuous graph. So that's no big deal. We got that fine. Okay. So, what about on this one? It's kind of a crazy equation, right? What about if I asked you, I can ask you the maximum number of x-intercepts. We got that. It's 8. But what if I asked you to find those x-intercepts? Do we have a method for finding x-intercepts when it's an x to the 8th? The answer is not really, okay? We would have to be able to factor out x's over and over and over again until we get down to where we can solve them. So whenever it gets complicated like that, you're going to have to use a calculator. And that's not the point of this class. So I'm not going to get crazy in depth with that. Probably the biggest degrees you're going to have to actually solve and find x-intercepts for is going to be about a 3, okay? So just so you know, x-intercepts, you're going to use your calculator for that, okay? We're not going to do big examples like that in here, really, okay? And then real quickly, an interesting notation, y-intercepts, let's just say the number of y-intercepts. How many y-intercepts? Like if the y-axis was right there. There should only be a maximum of 1, right? Now, it doesn't have to cross the y-axis. Graphs don't have to cross the y-axis. But if they do, and they're a function, there's only going to be 1. And this guy says he's a function. Why do I know there's not going to be 2? Because in order for there to be 2 y-intercepts, it would have to double back on itself, right? The graph would have to double back on itself. And that would not pass the vertical line test, right? So that's not a function. So we're not going to deal with stuff like that. So all of our stuff that we deal with, for the most part, it's going to be functions, and it's going to be stuff that we'll be able to say for real. This guy has 1 y-intercept. So don't stress out about anything crazy or whatever. We're not going to do weird stuff like that. Okay. So real quickly, I just want to throw this in here, and then we'll be done with this section. Yay, this is a lot shorter than the one on quadratics. How do we know if we have a polynomial that is quadratic? Okay, Remember that from the last video. That means that it's like y equals ax squared, da 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 da, right? All that stuff. Okay, so the largest exponent on the variable is a 2. Okay, then how many x-intercepts? And I told you we'd talk about this a little bit later. Okay, and now's the time. Okay, so there's either 2, 1, or 0. Okay, um, and the reason for that, I'm going to give you examples of all 3 of them. Okay, so the graphs are going to look something like this. Okay, we've got an x and a y, we've got an x and a y, and we've got an x and a y. Okay, so you're going to have 3 different graphs, and for quadratics, remember those are parabolas. I'm going to make all these facing up, upward turned parabolas. This guy would have 2 x-intercepts, right? Okay, and then this one would have 1 x-intercept. Okay, so 2 x-intercepts, 1 x-intercept. And this guy, because he starts up here and he only goes upward, right? He's going to have 0 x-intercepts, right? None. He doesn't cross the x-axis. He starts above the x-axis and he only goes up. You could also have one, by the way, that's like down here. It could be start below the x-axis and go downward. And again, he still doesn't cross the x-axis, so he would still have 0 x-intercepts, okay? So these things happen, and we end up with the 3 different options. You can have 2 x-intercepts, 1 x-intercept, or 0 x-intercepts. So just real quickly, I want to make sure we know how in the world does that happen? How do we know what's going on? Okay, so let's take a look. And to do this, what we're going to do is we're going to focus in on the quadratic formula that we talked about the other day. Okay, so the quadratic formula, if you remember, and hopefully you've used it a lot of times and it's kind of in the back of your head somewhere. Whenever I was in, whenever I taught high school, I always made them sing it to Pop Goes the Weasel, right? So there's a song. You can look up, there's lots of songs for the quadratic formula, but basically, Pop Goes the Weasel. X equals negative b plus or minus the square root b squared minus 4ac all over 2a. Oh, there you go. That's your entertainment value for the night. Okay, so Pop Goes the Weasel. That's the tune to it. I've actually heard people do Twinkle Twinkle Little Star, but I always did Pop Goes the Weasel. So anyway, there you have it. Isn't that Pop Goes the Weasel? Yeah, yeah, yeah. Okay, so anyway, quadratic formula. There it is. 3 different things can happen here. Okay, and it's all based on what's going on inside of this radical. I kind of alluded to that the other day whenever I talked about the vertex, right? Okay, so we talked about the formula of the vertex, and I said, what if that got 0? Okay, so everything that goes on with the number of x-intercepts that we have right here, 1, 2, 1, or 0, has to do with this guy. It's called the determinant because it determines stuff. I know, mathematicians. Okay, so there's 3 cases. Okay, what if this number is a positive number in the square root, in the radical? Okay, if it's a positive number inside of here, we've done a couple of those, right? It might be like 2 plus or minus the square root of, let's say, 16. Okay, square root of 16, we get a 4. 2 plus or minus the 4, let's just say divide by 2. Okay, the a is a 1 or something like that. I don't know. Okay, so but the idea here being is that 2 plus or minus the 4, those are real numbers, right? I'm going to get 2 real numbers here. Okay. If it's a positive number inside of the square root. If that's the case, then my solutions, remember these are my x-intercepts I'm finding, are my solutions. There are two of them on the real number line, right? That's what that is. It's the real number line. Okay, so if there are two, if it's positive inside of that radical, then I get two real numbers. I get two solutions. Huh, okay. Well, what if it's negative? Negative number inside the square root. Now, we haven't talked about this yet, but except for when we deal with the domain, right? But we'll have two imaginary numbers, right? So, like, say it was the square root of 4i in there. Remember, square root of 4i, that would, or I'm sorry, square root of negative 4, because it's a negative number in there, then I'll get 2i, which is two imaginary numbers. Okay. Okay. Well, in this particular look, hey, if there's two imaginary numbers as my x-intercepts, that means they're not crossing the real axis, right? Real number line. So that is 0 x-intercepts. Okay, there aren't any x-intercepts because they're all imaginary, right? No big deal. Okay, so we've got positive numbers, we've got negative numbers. What's the other option for inside of the radical? 0, Dr. Webster. So what if it's a 0 inside of the square root? Okay. Well, if it's a 0 inside of the square root, that means all this plus or minus stuff goes away, right? And that's where I get negative b over 2a. Well, hang on a second. That's the formula for the vertex, right? And that's where I get exactly one x-intercept, okay, or one solution. Okay, so this is one real number solution. So we get one x-intercept. That's hard to read there, I'm sorry, but it's one real number solution. I know. Just use the hashtag. Okay, that's a number sign, not a hashtag. So that gives me one x-intercept. Okay, so that's what's going on whenever I'm dealing with quadratic equations here. Okay, which are a specific type of polynomial. We actually already dealt with them, but this is just a little more in depth about why it's doing what it's doing. Okay, that's the truth of the matter. So yay, we have it. Okay, so really that's about it for our polynomial functions. This is only the first half of the homework for this section. Like I said, we will get into the rationals. So that's your next video. All right, thanks. Let me know if you have questions.